Welcome to the WattSherpa podcast, your guide to energy efficiency and savings.
I am honored to speak today with Dr. Brad Marston, a global leader in the physics community who has focused on climate science for over 2 decades. Dr. Marston has been a member of the Brown Physics Department since 1991, and he received his bachelor's degree from Caltech and his PhD from Princeton. He did his postdoctoral work at Cornell and was a visiting scientist at the Institute for Theoretical Physics at UC Santa Barbara, a visiting professor at MIT and ENS Lyon, a visiting associate at Caltech, and a general member of the KITP. Professor Marston is a fellow of the American Physical Society, where he is currently vice president and will become president in 2026. He's also director of the Brown Theoretical Physics Center. So, Dr. Marston, thank you so much for joining me today.
Thank you, Carter, and it's a pleasure to be here.
So, I understand that you were initially trained in condensed matter physics, but began working in climate science about 25 years ago. In addition to your research, you've also been actively involved in environmental advocacy, serving as the chair of the Sierra Club of Rhode Island. Could you share what inspired your commitment to environmental issues and shifted your career focus toward climate science?
My brother, who is 10 years older than me, is a physical geographer, and he's always been concerned with the physical environment. I think I picked up on that from him, and also from growing up in California, spending a lot of time outdoors, hiking, backpacking, and so on. I grew to appreciate the natural environment and could see some of the threats to it from human beings. I've had this concern for some time about the environment. And when I was a graduate student at Princeton was when Jim Thornton from NASA gave his famous testimony to Congress about the reality of global warming. I think that was in 1988. And that had a big effect on my direction.
Today, I'd like to talk about your work in quantum physics and how it's applicable to climate change. To start, could you help define generally what quantum physics is for our audience of students and environmentally focused consumers?
Sure. Quantum physics is generally the physics of the very small. That's the most common place where one encounters it. For example, the physics of electrons in atoms, how they behave, was famously a quantum problem that it was impossible to understand with classical physics. This led to a kind of crisis in classical physics that was only resolved 100 years ago with the quantum theory. And in the case of climate change or just understanding climate of planets, then that really harkens back to the very beginning of quantum physics, which was Max Planck's attempt to understand the radiation given off by material bodies when they're heated up. So say you have a piece of iron and you heat it up in a fire until it starts to glow red and it's giving off electromagnetic radiation. That couldn't be understood properly within classical physics. And Max Planck and then later Albert Einstein provided the basis for understanding that simple physical fact. And Einstein realized that that meant that light was composed of particles called photons. And he found a very simple relationship between the energy of those photons and their frequency. That's an equation that we can say is E equals HF. And it deserves to be even better known than E equals mc squared that most people associate with Einstein, because it's a really deep understanding of the universe. It relates the frequency S of a wave to its energy, the energy of a particle. So it talks about waves and particles, and that's what quantum mechanics is all about. So we need that basic understanding just to get to the most simple model of the Earth's temperature. And then that provides a starting point for understanding the effects of carbon dioxide in our atmosphere.
Speaking of waves, like you said, a very important part of quantum physics. I know recently you and your colleagues made a connection between topological insulators and ocean waves along the equator. Could you share a little bit about the importance of that discovery?
Sure. Quantum mechanics, as I mentioned, has a wave-like aspect. And electrons in quantum materials like semiconductors, silicon, for instance, have a wave-like property. And it was discovered several decades ago that when you take a semiconductor and put it in an intense magnetic field, that the current that flows through the material is quantized. And that is, it undergoes jumps to very specific values. And we call that the quantum Hall effect. And several Nobel Prizes have been awarded for the fundamental discovery of this effect and then its theoretical understanding. We realize that there are waves in the fluid Earth system, that the mathematics that describes those waves is rather similar to the mathematics that describes the electron waves in the quantum Hall effect. And in particular, the equator of the Earth functions as a boundary, of course, between the two hemispheres, the northern hemisphere and the southern hemisphere. And right at that boundary, there are waves that propagate in both the ocean and in the atmosphere in one direction only. They just go from the west to the east. And those waves are called Kelvin waves and Unit waves. And they had previously been identified as an important component of the largest climate oscillation that we experience on the timescale of a few years, which is the El Nino Southern Oscillation. That equator is a lot like the edge of a quantum Hall system, a semiconductor that's carrying current along the edge of the material. And the magnetic field, in the case of the quantum Hall system, is very similar to the effects of rotation in the Earth. As the Earth rotates once a day, it has the famous Coriolis force that deflects motion. And we realized that there was this mathematical similarity that allowed us to borrow the mathematics that had been applied in this quantum realm and apply it to the fluid Earth system.
It's really interesting to hear about discoveries like this because I feel like sometimes a lot of skeptics of research in certain STEM fields that may not seem directly useful for everyday life end up leading to discoveries like this that end up being integral for helping just humans in general. So it's really interesting to hear. Thankfully, much of the world is now recognizing the impact of climate change. However, some people still reference the natural warming and cooling cycles of the Ice Age or things like the Little Ice Age. Based on your research, how can we demonstrate the impact of human activity on global warming?
So that's a good question. People who say this is just a cycle, the Earth goes in warm and cold phases and so on, don't appreciate the big disparity in times that this happens. So the last ice age peaked around 20,000 years ago. And so if we think about that in terms of human generations, that's 1,000 generations ago. But the warming that we're seeing right now is occurring over a single generation. So it's a huge difference to compare the ice ages to the global warming that's being observed now. And if you think of it as like a timeline, if you stretch the timeline out over the distance of a football field and say that represented those 20,000 years of since the last glacial maximum, then the amount of time that's passed since, say, the 1970s, 80s, when Jim Hansen was starting to talk about the appearance of global warming, and that's like just a few inches or something at the end of that huge time scale. So it's just a huge difference in how much time has passed. And of course, the Earth has had climate change on all sorts of time scales, even going back much further. There's even more drastic climate change has happened. But the kind of climate change we're seeing right now is very sudden, and living beings have difficulty adjusting to such sudden changes.
So, like you're saying, even though we've known about human caused climate change since the 70s, 80s, and even before, I know that in 2012, you co founded the Topical group on the physics of climate for the APS, which was unfortunately during a period when many were still questioning the science of climate change. Could you share how the group has evolved since then and how it's doing today?
Yeah, when that group came together, it basically brought together two groups of physicists, mainstream climate thinkers like me, and people that were more skeptical about climate change. Right? Tended to be older physicists. And they were really upset that the American Physical Society had adopted an official position declaring that climate change was real and a problem. This group came together and it was rather difficult, I would say, for the first couple of years, but it has matured since then and is now really taking on a leadership role in climate physics. That is the idea that physicists have some particular skills, talents that can contribute to this broad area of science, climate science, probably most interdisciplinary of all areas spanning from ecology to geology, astronomy, fluid dynamics, and so on. It requires the efforts of scientists across many fields and also social scientists too, because human behavior is certainly involved. And no one area has the answers to everything, but by working together, then we can gain a better understanding of climate, how it is currently, how it may change, and perhaps how to address some of the effects of climate change.
It's really interesting to hear you say that because I agree that if there's one thing that I've learned from creating this website and conducting multiple interviews, it's that the climate issue is such a multidisciplinary issue and it requires a wide span of experts from multiple areas. So it's great to hear that a lot of progress has been made on that even in the past 10, 15 years.
Yeah, I'd like to
Um,
touch on something that you mentioned earlier, which is the value of peer research. So often scientists are asked, how does this help in make a new product or to enrich us or something? But most scientists, I think, are driven by just a curiosity about nature. And it doesn't necessarily have to lead to anything practical. And for me, the climate system is this wonderfully rich system with lots of amazing things happening that teaching us all sorts of interesting physics, other areas of science too. And by stepping back a little bit from always focusing on the problem of climate change, which is certainly a problem, but just taking a little bit broader view, then we can come to appreciate the climate system as this amazing thing and perhaps have a more open view towards the world and how it functions and appreciate it more. And that may by itself help spur additional efforts by people to preserve the environment.
And I feel as I've done even more research into climate systems and things like that, it's just amazing how much we know, but also how much there is still to learn and how much we still don't understand. There's tons of people who are driven to discover these things and learn more about these systems.
Yes.
I know that you're also a member of the panel on public affairs at the APS. Could you talk about how physicists are helping to impact public policy?
All right. So the panel on public affairs looks at different issues where physicists may be able to make a contribution. And I'll just illustrate that by something I've been involved with, which is the writing of a report on an overview of different technologies, different approaches to remove carbon dioxide from the atmosphere. So this sometimes goes under the acronym CDR, carbon dioxide removal. And the idea is that we're still emitting a tremendous amount of carbon dioxide in the atmosphere. In fact, I think this last year was the highest rate ever. And the IPCC, the Intergovernmental Panel on Climate Change, has concluded that it will be necessary to actively remove carbon dioxide from the atmosphere. Even if we were able to slow down the emissions very quickly, we still have to remove carbon dioxide from the atmosphere in order to keep the temperature from exceeding 1.5 degrees, probably, or we're going to go well past that. We decided that we would take a physics perspective to understanding the different technologies. There's a wide range of things. Some companies have built machines that do something called direct air capture. They're using chemical processes to remove carbon dioxide from the air, blowing the air through. There's a plant up in Iceland that's powered by geothermal energy that's doing that. Then there's other approaches that are based on using materials in the natural environment and trying to use those to remove carbon dioxide. So an example of that is enhanced rock weathering, where you take a rock like basalt, basically from volcanoes, and grind it up finely and spread it over vast areas of farmland. And it can enrich the soil and then also react with atmospheric carbon dioxide to remove it from the air. So we took a physics perspective on this. There are other groups, other efforts have been made, certainly to take an overview of all the different technologies, but our perspective was that of physics. And so we emphasize the laws of thermodynamics, the fact that there's a certain minimum amount of energy that would be required to do this direct air capture. And so it's a tremendous amount of energy that's required, and that's a limiting factor. Or in the case of this rock weathering or related approaches, which we call once-through technologies, you need a tremendous amount of material. So you're mining, say, rock in the same kinds of quantities that we've extracted coal and oil from the earth in order to do this removal. And so none of these things are easy. There's no easy solution. And we're just emphasizing that. We're just pointing that out, that this is an option, perhaps. There's lots of questions about how these technologies will work, how well they'll work. But implementing any of them at this kind of scale you would need to remove carbon dioxide from the atmosphere is going to be a massive undertaking. So like with the plant in Iceland that just opened, you would need 1 million of them to remove all the carbon dioxide that we're adding to the atmosphere each year. And so it's just mind-boggling the scale that's required.
Yeah, that is crazy. Wow. It's great to hear that policy is being shaped with true science backing behind it. I think without that, we're really left in the dark. So it's great to hear that work, whether it's positive or negative, advice is being given.
Yeah, this report, by the way, should be coming out in the next couple months. It's completed and approved, and it's just going through the final process of typesetting and so on. It'll be publicly available if anyone's interested.
So at the start of the interview, I mentioned that you will become president of the American Physical Society in 2026. And I wanted to ask what your future goals are for the organization when you take on that very impressive leadership position.
Yeah, I was elected as vice president, but it's really a 4-year commitment. So each vice president becomes president-elect, then president, and past president. And each president has a theme for their year. So the president right now, Young-T Kim from the University of Chicago, is a high energy experimentalist. And her theme has emphasized international cooperation among scientists, because high energy experimentalists they're often working on these very large experiments like at CERN, and they have to cooperate in order to achieve their goals. The next president, John Doyle from Harvard, works with quantum physics. And so his presidency coincides with the International Year of Quantum Science and Technology. It's the 100th anniversary of the papers by Heisenberg and Schrödinger. And so next year will be on quantum physics, basically. And my year, I will want to emphasize climate change and sustainability. So this is something that is of great interest to the members of the American Physical Society. When we do surveys, it ranks as the top area of interest among physicists, even exceeding research funding. And so I would like to explore during 2026 different ways that physicists can contribute to an understanding of climate change and also to developing sustainable ways of living and producing energy, for instance.
That's amazing to hear. And I'm sure that year is going to create so much productive work for figuring out different solutions to climate issues and finding new developments.
I hope so. Yeah.
So, shifting to technology, I'd love to hear your perspective on how advances in AI and quantum computing could impact your research. I know today's supercomputers can handle lots of complex climate models, but AI can improve data processing, and quantum computing can solve problems in hours that take years today. So, how do you expect this technology to enhance your work?
Yeah, so definitely a form of AI known as machine learning is playing a rapidly growing role in science and in climate science in particular. So, problem, for instance, that climate models have is not being able to resolve all of the processes that are going on. If you have a global climate model, it's just impossible for a any present day computer to follow every cloud, and uh, so there might be ways of understanding this problem in a statistical way, and machine learning can provide some uh, tools for developing these statistical descriptions of these small scale processes that are reliable. And so a number of groups are investigating that. And they're also, of course, using machine learning to analyze data that's collected from satellites, observational stations, and so on to get a better picture of the climate system and how it's changing. So that's very much a real thing. Uh, the quantum computing is much more in its infancy, and it's not even clear that it will contribute in a useful way. It may, and I've been doing a little bit of work using a quantum computer built by IBM to simulate what we call a toy model of climate. It's really a very simple model, one that's so simple that you can solve it on a piece of paper analytically, giving us an exact solution. But we wanted to test that exact solution against the quantum computer. It could just barely do something there. People are working really hard on quantum computers, and there are some problems where it seems that if you had a sufficiently powerful quantum computer, it would have a real advantage over a classical computer, such as the factorization of large numbers. But it turns out that for many of the problems that we're interested in, it's not obvious that even if you had a really powerful error correcting quantum computer, that it would be an advantage over classical computers. Just trying to establish whether in principle that is the case is an important problem.
It's interesting the different perspectives on the technology. I love hearing, both sides of the argument, like how useful they can be. Do you think one day the technology will be advanced enough that we could get something like perfect weather forecasts, or are you doubtful about that?
I think weather forecasts will always be uncertain because of the fact that the weather system's chaotic. It basically is essentially a proof that goes back really to Ed Lorenz, discoverers of chaos, that you will never be able to predict the weather more than a few weeks in advance, because any slight change in the initial conditions, the observations or the model imperfections will grow over time and blow up the forecast. But climate is quite different because it's a statistical description of the weather. And so that's where our quantum computing idea comes in, because quantum computer based on quantum mechanics, well, quantum mechanics is a statistical theory, a statistical description of reality. So we're trying to use the quantum computer to directly get at the statistics of a model weather system. That's the basic idea. So I think we will be able to get more and more reliable climate projections, even though
Yeah,
the weather will always elude our grasp. And probably the biggest source of uncertainty in the climate projections will actually be human behavior, because if we're saying this is what it's going to be like in 100 years, that's all based on assumptions about how human human beings will behave, how civilization will develop, and so on.
that's interesting to hear because I never really thought about it that way. But as humans are having a greater and greater impact on climate, I imagine it's become harder and harder to predict what the range of effects could be in the future.
Right.
It's interesting.
Yes.
So, commenting on another one of your projects, I know that you are part of a research group that recently received a grant from the Department of Energy for a study related to offshore wind energy that focuses on floating wind
Right.
farms. There's a lot of variables to consider in the interactions between air and ocean currents. I was wondering if you could share a little more about that. And again, going back to quantum computing, if you think it's possible that technology like that could be ready to help with this analysis in the near or long term.
These floating wind turbines are different than the ones that are being built off the coast of New England, for instance. Those ones are anchored into the ground because the continental shelf is rather shallow. The water is quite shallow, say also Cape Cod, and you can anchor the things directly in. But off the West Coast in California, the continental shelf drops off very quickly. And so these things will have to be floating, and nobody has really built them at the scale that's necessary yet. Norway has some floating, but these things are going to be enormous. They're going to be something like 900 feet tall. They can't be built, for instance, in the San Francisco Bay Area because they won't fit underneath the Golden Gate Bridge. In fact, they're taller than the towers of the Golden Gate Bridge. And so then you can imagine these things out in the ocean, they're going to be rocking back and forth as the waves are hitting them. And then the atmosphere flowing over the ocean is affected by the waves, and it's affected by the moisture of the ocean. And there could be fog, all sorts of variables there. So it's a very challenging approach to understand, for example, what is the optimal configuration of a farm of these wind turbines. Again, we're trying to take a statistical approach to this. We don't want to model every little eddy of turbulent wind, for instance. So we've been developing for some years what we call direct statistical simulation to get at things like average power in this case. That we've applied it to very simple problems. And now we want to scale up these tools to these much more realistic scenarios. And so we can't possibly do that just by ourselves. Our group includes people who are doing wind tunnel experiments, doing observations of the atmosphere from drones, doing very high-powered computer simulations on supercomputers. We're all talking together, and we're going to also be using some machine learning techniques. I don't think quantum computers will be able to contribute over the time frame of our grant, but possibly in the future, if it appears that they really can beat classical computers in these types of problems. But again, I emphasize that that's really an open question. We don't know. There's lots of things we don't know. So there's lots of questions for young people like you to work on if you want. There's no dearth of those.
Yeah, obviously the work being done here is extremely innovative. It'll be interesting to see where technology like this goes and what ends up coming out on top as some of the major energy producers in the near or long term future. So very interesting. I've got just one more question about innovation. I've seen reports about technology that can block the sun by spraying reflective particles high in the atmosphere or making clouds brighter.
Right.
Do you think these could be effective methods for cooling the planet, or would they have negative side effects?
Yeah, those technologies go under the name of solar radiation management. Basically, try to find ways to reflect sunlight back out into space. And there's also an idea to maybe thin cirrus clouds to allow infrared radiation to escape to space more efficiently, cooling the planet. So, but basically, in both cases, one's trying to change the flow of radiation between the Earth and sun and space. And so the answer is, I think some of these would work in the sense of cooling the Earth, but they might do all sorts of other things that are undesirable. And right now, the research on these approaches is in its infancy, and trying to figure out how this could be done safely is a challenging thing, especially if you aren't actually doing experiments. But you might not want to do experiments because people may get upset that you're tampering with the climate system. Of course, we're already massively tampering with the climate system, but this would be on top of that. This would be a really deliberate thing. So I think we want to move cautiously and consider all the ethical issues around these kinds of approaches. Probably the easiest thing to do is to inject particles up in the stratosphere, sulfur dioxide, that will reflect sunlight. And it probably could be done relatively inexpensively, at least certainly compared to the other technologies I was talking about earlier on carbon dioxide removal. But this really opens up all sorts of moral dilemmas. For instance, some polluting industries could say, we can go on polluting because we can just create ever thicker layers of reflecting particles up there. And that would really be a disaster because it's not getting at the root problem. And also, let's say there's some economic upheaval and we stop putting stuff into the atmosphere to reflect this light, then it will fall out after a few years. And then the Earth would be hit with a massive surge of heating due to this elevated carbon dioxide that remains. The carbon dioxide stays up there for hundreds of years, thousands of years, whereas these particles fall out. And we don't know what effects those particles might have on the stratosphere in other ways. We're already doing inadvertently some experiments, I think, along these lines, because I learned at a recent meeting, the American Meteorological Society, that all the rocket launches to launch satellites, that's been increasing, and like SpaceX sending up these clusters of satellites. When these rockets parts burn up in the atmosphere, they're typically raining down aluminum particles, aluminum oxide. And so one poster I was reading at this meeting was noticing that if the number of satellite launches continues to increase, then this might start to have some global effects on the stratosphere and the climate system. And it's these kinds of surprises that we really need to watch out for.
I feel like it's such a delicate balance because you don't want to tamper with a natural system that's so delicate like that without being extremely cautious.
And you could also make the converse argument that doing nothing is itself a risk because as we are starting to see some pretty extreme climate events like the floods in Spain and in other places around the world, probably some of that is associated with the added moisture in the atmosphere. As the atmosphere warms, it can hold more and more water vapor, about 7% more for every degree Celsius of warming. Inaction also can lead to problems. And so it's a difficult moral question. It's also a difficult international question because a single country could decide that it's going to go alone and start modifying the stratosphere. And that will affect the climate worldwide, though. And so some countries may feel that it harms them more than others. It's really a can of worms.
Yeah, I'm hoping that although each of these events are tragic, I'm hoping that people seeing the actual effects of climate change come into reality. It might be an awakening for some people into what we need to do to stop further issues like this.
Yeah, perhaps. Yeah.
So, for my last question, I would love to get your career advice for our audience of students. You've said that climate science is the most interdisciplinary science, and I think this interview has really proved that. For young people with a passion for science and the environment, is there an academic path that you would recommend we pursue?
There are, I think, many possible paths. As I mentioned, pretty much all of the sciences have something to say about the climate system. And I include the social sciences in that too. Unfortunately, there will be certainly job opportunities in this available because of the problem is just going to get worse before it gets better. And I think that there will be a longstanding need for people to think about the climate system, think about sustainable energy systems, think about maybe how to repair the climate system. And those needs will just grow. So even now, there are many jobs in academia in the climate sciences, and it's a growing field. It's been growing at my university, but also lots of other universities. People recognize how important it is. I think if I had any advice, it would be to follow your bliss, follow what you find you're most passionate about. And perhaps it's physics, perhaps it's geology, perhaps it's engineering, perhaps it's something in political science. So people learning how to cooperate with each other better. All these avenues can lead to a foundation for contributing to climate solutions. And the most important thing, which is something I tell my daughter all the time, is to find out what you're passionate about and follow that.
And I think it's true that we really can have the most impact when you follow what you love, because truly each area of expertise can contribute in their own way to understanding climate systems and climate change. Um, so-
Yeah. And if you're doing science or engineering, if you're doing something you love, then you'll be thinking about it all the time. And it's maybe in the off moments when some new insight might come to you. So if it's something you don't like and you're treating it like a 9 to 5 job, so you go home and you forget it, stop working on it, watch TV or something, then that's fine. But if you're trying to advance our knowledge, advance our solutions to climate change, then it has to be something that you're really thinking about all the time.
Dr. Marston, that was all the questions that I had for you. Thank you so much for taking the time to help simplify lots of very complex issues and topics. I appreciate your time and all the insights that you shared. For anyone that's watching that's interested in learning more about Dr. Marston's work, I'll share a link to the Marston Research Group website in the notes. You can also just search for Dr. Marston on YouTube, and you'll find a bunch of great lectures diving deeper into today's topics. So once again, thank you, Dr. Marston.
Thank you, Carter. It's been a pleasure talking to you.
If you enjoyed our podcast, please like and subscribe and visit us at WattSherpa.com.